In previous lectures, we have seen the dynamics for the single particle, in which we have seen the law of conservation of the linear momentum, angular momentum, and the law of conservation of the energy for the single particle. And also we have seen dynamics of the system of the particles, in which we have previously seen law of conservation of the linear momentum, angular momentum, and the conservation of the energy for the system of the particles. So in this lecture we are going to start with the law of conservation of the energy for the system of the particles. So let me write it here. So let us consider a system in which number of particles are there, and as we have already seen that in a day-to-day life we don't come across with the examples of the single particle. So whenever there is a application level, we deal with the system of the particles. So the dynamics of the system of the particles is at a higher application level. Suppose there is a system of the particles which consists of n number of particles, and if the force applied on the system, we call it as a F external, and there is also internal force between any two particles of the system. According to the Newton's third law, there is an equal and opposite interaction between the ith particle and jth particle. Suppose the system consists of n number of particles, like starting from which having masses m1, m2 up to mn. If I consider any particle randomly, I will call it as a ith particle. So this is a style of the physics which says that if you consider any particle, call it as a ith particle, rather than saying as one particle, second particle, third particle, like this. So if I consider the ith particle, so for this ith particle, the total force applied will be given by F is equal to F external plus F internal. And as we are dealing with a single particle I, so it will be Fi external, Fi internal, and this will be the total force on the ith particle. And as we know that this internal force is 0 due to the interaction, because the if suppose this is the ith particle and this is jth particle, so whatever force is applied on this ith particle by the ith particle on the jth particle, equal and opposite force is applied by the jth particle on the ith particle. So F internal I is equal to minus F internal J. So these interaction forces are equal and opposite, and they will cancel out each other. Therefore, total internal force acting on any particle will be 0. Therefore, the total force now acting will be Fi external. Now, if I take the total force acting on the whole system, so I can write this F. So we are considering for the whole system, therefore we have removed this I. So it will be summation of Fi external, where I runs from 1 to n. Suppose the system consists of n particles, and if I collect the external force applied on each and every particle externally, and if I take summation of that, then that will give me the total force on the system of the particles. Total work done by the system or on the system. So this total work done will be equal to summation of integration from 1 to 2 into F into dr. Now this is a total force for the system of the particles. We know that this dv is equal to dr upon dt. So this is the definition of the velocity, rate of change of displacement with respect to time, and I can write this dr is equal to dv into dt. According to the Newton's second law, we know that F is equal to dp upon dt, and therefore I can also write this as d by dt of mv. So let me just put the value of this F and this dv into this equation, and therefore this equation will become summation of integration from 1 to 2 d by dt of mv into this dv into dt. So this dt will get cancelled. So it will be summation integration from 1 to 2 m into dv into dv. So it will be summation of integration 1 to 2 m dv square, and if we solve this we are going to get 1 half m v2 square minus 1 half m v1 square, which is nothing but equal to T2 minus T1. So this T2 is the kinetic energy of the final position minus the kinetic energy of the first position. According to the another definition of the force can also be written as this gradient of this potential field F is equal to minus delta into V. We are considering for it ith particle, so we can write it as a delta Vi. If I want to calculate the work in a form of the potential fields, now this is a total work, so I can write it as a summation over integration of minus delta Vi into this dRi, and the summation is running from 1 to n, and this integration is running from 1 to 2. 1 and 2, these are just the positions of the system from when the system is moving from position 1 to position 2. Now if I solve this, we are going to get, this is nothing but the V will be there from 1 to 2, V2 minus V1 minus of this, so it will be V1 minus V2. So this is W. This is a work in a form of the kinetic energies. So this is W is equal to T2 minus T1. Similarly, we have also got the work in a form of the potential energies, which is V1 minus V2. Now comparing these two equations, we can say that T2 minus T1 is equal to V1 minus V2, or we can say that V1 plus T1 is equal to V2 plus T2. This is the law of conservation of the energy for the system of the particles, which says that if the external forces acting on a system of the particles are conservative, then energy is also conserved in the system of the particles.